The paper Rationalizing the Time Delay Neural Network Architecture by Michael I. Jordan was published in 1986. The paper introduces a new type of neural network called the recurrent neural network. Recurrent neural networks are a type of neural network that can process sequential data. They are made up of a series of nodes that are connected to each other in a loop. This allows the recurrent neural network to remember previous inputs and use them to generate outputs. The paper begins by discussing the limitations of traditional feed-forward neural networks. Feed-forward neural networks can only process data that is presented to them in a single batch. This makes them unsuitable for processing sequential data, such as text or speech. Recurrent neural networks overcome this limitation by allowing the network to remember previous inputs. This allows the recurrent neural network to learn long-term dependencies in the data. The paper demonstrates this by training a recurrent neural network to predict the next word in a sentence. The recurrent neural network was able to learn the long-term dependencies between words, and it was able to predict the next word with high accuracy. The paper also discusses the challenges of training recurrent neural networks. One challenge is that recurrent neural networks can be unstable. This means that they can oscillate or diverge during training. The paper proposes a number of techniques for stabilizing recurrent neural networks, such as using gradient clipping and momentum. Overall, the paper provides a clear and concise introduction to recurrent neural networks. The author demonstrates the effectiveness of recurrent neural networks on a number of tasks, and discusses the challenges of training recurrent neural networks. The paper is a valuable resource for anyone interested in learning more about recurrent neural networks and their applications. Some additional details about recurrent neural networks are: 1. Recurrent neural networks are a type of neural network that has feedback loops. This means that the output of the network can be fed back into the input of the network. 2. Recurrent neural networks can be used to process sequential data. This means that they can be used to model data that has a temporal order, such as text or speech. 3. Recurrent neural networks can be used to learn long-term dependencies. This means that they can learn how the output of the network at one time step depends on the input of the network at previous time steps. 4. Recurrent neural networks can be used to solve a variety of tasks, such as language modeling, speech recognition, and machine translation. The challenges of training recurrent neural networks are: 1. Stability. Recurrent neural networks can be unstable during training. This means that they can oscillate or diverge. 2. Vanishing gradients. The gradients of recurrent neural networks can vanish during training. This means that the network can become difficult to train. 3. Long training times. Recurrent neural networks can take a long time to train. This is because they need to learn long-term dependencies in the data. Despite these challenges, recurrent neural networks have been shown to be effective on a variety of tasks. With careful training, recurrent neural networks can be used to achieve state-of-the-art results on a variety of problems. The contributions of Michael I. Jordan's paper are: 1. The paper introduced the recurrent neural network architecture, which is a fundamental building block of many modern deep learning models. 2. The paper demonstrated the effectiveness of recurrent neural networks on a number of tasks, such as language modeling and speech recognition. 3. The paper proposed a number of techniques for stabilizing recurrent neural networks, which have been used in subsequent work. The paper by Michael I. Jordan is a seminal work in the field of recurrent neural networks. It laid the foundation for the development of recurrent neural networks as a powerful tool for processing sequential data. The paper's contributions are still relevant today, and they continue to be used in the development of new recurrent neural network-based models.